Thank you to the organizers for the nice opportunity to come back here. I love this school. I think it's really important. It's a great opportunity, and I really enjoy coming here. So the title of my talk is Design and Synthesis of Intermetallic Crystals. That may be an overstatement. And what I'm going to talk about are induction furnace and arc furnace methods. Before I start, I want to just say that this work or these apparatuses all exist in my lab down at the National High Magnetic Field Laboratory. We're funded by the National Science Foundation. And then also, a lot of the funding that we have comes from the Department of Energy in the form of an Energy Frontiers Research Center called CAST, which is the Center for Actinide Science and Technology. So a lot of our interest is in actually the chemistry of transuranics. But this also spills over into some F-electron physics like lanthanides and so on. So I'll tell a little bit about that, and I'm happy to talk about it a whole lot more afterwards if anyone's interested to learn about that. Okay, so just a brief snapshot of my group to give some sort of introduction. At the moment we have 4 graduate students, 1 postdoc. We also work with undergraduates like a lot of people do. And then one of my favorite things is that we also mentor middle schoolers, usually 1 semester each year. And so in the lower left-hand corner are some recent participants in that project. And we even have them doing synthesis in the lab, at least on projects that are pretty safe to actually do. Okay, so what are our interests? Well, like I said, we're interested in actinide waste forms. Our job in this project is to try to develop waste forms that would deal with some pretty unpleasant actinides. I think everyone knows that the United States and the world at large has a lot of nuclear waste, and we don't exactly know what to do with it. Some of that has to do with separations chemistry. For instance, curium and americium are hard to separate chemically. But also it's just a question of, what sort of crystalline or otherwise, glass or salt or whatever you want, form are you going to put actinides into so that you can reliably put them somewhere and trust that they're not going to get into your groundwater or something like that. That problem is really not well managed in the US or elsewhere, but we're trying. Okay, that gives us a way really to study F-electron valence physics. That's sort of a fundamental question in the area. The valence that you see in actinides for those F-electrons impacts things that are really simple, like what sort of crystal structure are you even going to get? But it also gives you a way to sort of go into things like sort of unconventional magnetism, sometimes superconductivity. We like looking at thermoelectric materials, quantum criticality, so on and so forth. And then, like a lot of people, we have a separate project that's looking at topological states of matter in all sorts of different types of materials. And since we're located at the Mag Lab, this sort of leads us to focus on measurements in high magnetic fields. It's an opportunity to look at things like Fermi surface topography, unconventional electrical transport, so on and so forth. But I'm not going to focus on really these sorts of things today. It's just to give you a sort of vague notion of what we're all about. Okay, so in my lab, we have these science motivators for what we want to do, but we have to have some tools to try to approach these problems. And so our sort of number 1 tools is trying to produce a bulk crystalline specimens of all different sorts. And I'm going to come back to this theme later on, but I think it's really important, when you're thinking about what you're going to grow, how you're going to grow it, that you have a large toolbox to try to draw from. And the reason for this is that different elements, or different chemicals, whatever, have different personalities. And so different techniques are going to be well suited to one thing, different set of techniques for another. So that's why we have sort of diversified, I guess you would say, in terms of synthesis methods. And then we do characterization that's fairly typical, including things like X-ray diffraction, some typical bulk measurements at high pressures, thermal expansion, and measurements in high magnetic fields. All right, so the outline of the talk is kind of like this. And I wanted to start with this, coming back to this idea that you want to develop different tools for different things that you're trying to accomplish. So this is a quote from this person, Charles Eames. I know absolutely nothing about this person, but I've been told he's a famous designer from the 20th century, okay? But he said something that I think is really relevant for what we're interested in, and that is that the problem of designing anything is, in a sense, the problem of designing a tool. And in designing a tool, it's usually wise to have a pretty clear idea of what you want the thing to do, and the need is to fill its particular objective. So again, you come with a science idea, you want to make something, but in order to do that the best way possible, you need to have this big toolbox, and you may even need to make a new tool, in order to get the thing that you want. And that's what we're about. Like, that's the whole point of doing crystal growth, I think. At least for physics. Okay. All right, so the outline of the talk. I'm going to start by making some general comments. As I was preparing this talk, I was thinking back to previous years, and there was some useful advice that different people had brought up. So I'll probably tell you some things that you've heard before, but it never hurts to reiterate. I'm going to bring to your attention some books that I think are really essential to have. I hope that maybe you already have them, but actually I wasn't aware of them until coming to this school, so I think they're really good. Then I'm going to go on and talk about induction furnace techniques, tell you what is the basic idea there, some applications for it. And then if there's time, I'll also talk about the arc furnace and some ways that we'll use it. So the arc furnace is part of the practicals here, right? So how many people have already seen the arc furnace? Okay, so like half of you, something like that. So now you're already experts in arc furnace techniques, but humor me and maybe I'll tell you something that you'd like to hear. And then before I really get started, I'd also like to just say this talk is really informal. Please interrupt me at any point that you have any sort of question, and I will just do my best to answer it, or maybe one of the other experts here can answer it too. So this room is much bigger than the previous room. But just, please do ask questions if you have them as we go. There's absolutely no need to get all the way through this talk. Okay, so general comments, general guidelines. Okay, so first thing I want to say is about starting chemicals. I think this is fairly obvious, but it bears repeating. It's really worth your time to know the properties of your starting chemicals. This includes obvious things like what is its melting temperature, what is the vapor pressure. And you really want to do the background work to know this, because if you're like me, you've probably put something into a quartz tube and sealed it and heated it up and caused it to explode. That can be avoided. So, know this sort of thing. But the other thing that I want to encourage you to do is to be fairly suspicious of your starting materials, right? Don't always believe what you read on the bottle. An easy way for an error to happen is that the previous graduate student who was working before you and has now finished mislabeled a bottle. And that happens, fairly often, I would say. But beyond that, I've heard stories from Brian Sales, for instance, that sometimes when chemicals come from the company, it's not even what it's labeled as, right? So I think you should look in the bottle, which you'll do, but have an idea of what it should be like, right? If you get something out that's supposed to be indium and it's not bendy, then it's not indium, right? So do your best to know, or have some reliance, some reliable sense of what your starting materials should be like and what they're going to behave like as you start to work with them. Okay, another thing that's obvious, but even I fail to do this all the time. Really write absolutely everything down. Take as many pictures as you can, be extremely detailed. And the reason for this is that, crystal growth really turns on the details. And, Judy was telling this already with, the position of the boats for, some of these growth techniques. I have another interesting story. This one's also from Brian Sales. He was attempting to do a flux growth of, I think it was manganese silicide, I don't remember. And he had this recipe that Paul Canfield would use, right? And Canfield could get these giant, beautiful, perfect single crystals. Brian would get tiny, high quality but tiny crystals. And that wasn't going to cut it for neutron scattering experiments. So he tried, he couldn't get it to work, didn't know what to do. At some point, he put a reaction into a furnace that was sitting on a drawer set, right, that has heavy drawers on it and tools in it. And at the end of that growth, they took out the batch, and to their surprise, there were really large single crystals in there. And they didn't know what made the difference, right? Like all the conditions were exactly the same. And it eventually occurred to them that what made the difference was that this thing was sitting on this heavy drawer set. People were taking tools in and out of it, all day. And so the furnace was being shaken all the time. Okay? That made the difference. And it turned out that Canfield's furnace was in a similar situation. So it really matters. You have to take all of the details down. And don't be like me and produce a nice batch of beautiful crystals and then not be able to do it again because you didn't take enough notes. Okay? That will absolutely make you very sad for your thesis. Okay. Okay, another thing, it's very useful, especially for bulk crystal growth, to weigh things at every step of the process. I'll give you one example. How many people are familiar with molten metal flux growth? Okay, a large enough fraction that this will be a useful story. Okay, so in molten metal flux growth, what you do is you take some low melting temperature element, you dissolve some higher melting temperature elements into it, you slowly cool it down after the liquid is supersaturated, and you'll get crystals that precipitate out. Then you may centrifuge away the flux. Well, it's useful if you know, obviously you're going to know how much starting material you had, but it's useful then to mass the entire batch yield, right? If the batch yield gives a mass that agrees with the amount of the thing that you were trying to make, you can be pretty sure that you made what you intended to make. If it is some completely weird number, it's probably not what you were trying to make, right? Maybe the flux is actually now part of the crystal. Maybe if it was an indium flux, now you have some indium containing crystal, right? So this gives you a hint immediately with no work whatsoever, to know what you've grown. I think that's important to do. Okay. I know yesterday you had a nice lecture on chemical phase diagrams. I think, always refer to your chemical phase diagrams before you start a growth. I've done many growths where I was hasty and I threw something into a flux and I assumed it would dissolve and it didn't, right? That's a waste of time and money, so don't do that. When possible, know the properties of your melt. Different melts sort of behave in different ways. They may creep over crucibles, they may attack crucibles, things like that. I'll come back to that a little bit later. It's useful to optimize your crucible material. This is, sort of directed towards bulk synthesis. I think a lot of people have encountered aluminum oxide crucibles, but there's, a whole zoo of other types out there, and I'll come back to that a little bit later. And then this is really important. I know you know this, but it's still a great way to make a mistake. Leave time at the beginning and the end of the day, and really don't rush yourself, right? So one of the main reasons I don't go in the lab as much as I used to is that I find that I can't do this for myself, right? But students can. And just to give you one more story, and I won't name any names, but JP knows who I'm talking about. In one of the labs that I worked in before I got there, there had been one student who did something to a furnace that he shouldn't have. He was also rushing at the end of the day. He started a reaction, heated the furnace up, and later on that night, the entire lab burned down. So this is really important, right? For your safety and the safety of everyone else. So, yeah, okay, I sound like a mother hen or something, but
It wasn't you.
it was not me. I did not make that mistake, and it scared me badly so when I heard about it. I just really want you all to be safe, so please keep that in mind. Okay, so here's just a few examples of ways that things can go wrong. This is a tantalum crucible. This was nickel. I like tantalum crucibles because they have very high melting temperatures, but it turns out there's a deep eutectic between tantalum and nickel. I could have known that very easily, but I was hasty. That's not good. Okay, know the properties of your melt. These are some tungsten and molybdenum crucibles where we were growing some, what was this? Some lead-containing thing, a lead-rich thing. We were doing a Czochralski growth. I'll return to that later. But what happened is that this was at a high temperature for maybe 12 hours, and the melt actually climbed out of the crucible and came down the sides. Right? So you can learn about these things before you start sometimes. And this brings me to this. So this is worth taking a screenshot of or ask me to send it to you. And actually Lucas found this, who's at the school here. This Liquid Metals Handbook from Oak Ridge National Laboratory is from the 1950s or something, but it is really useful. There's good information in there that is just not widely available, as far as I can tell. Okay, so if you want it later, just email me, and I think we have the PDF. Email Lucas. He has lots of time to respond to emails. Okay. 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 So another useful reference that I want to really bring your attention to is this book by Brian Pamplin. He was at the University of Bath in England. I don't know anything else about him other than that. But he wrote this really great book that lays out the basic principles for more or less every type of crystal growth that we do. Okay? And a lot of times, at least I had this idea, a lot of times it may seem like you're inventing a new way to grow something, being extremely clever. But to my surprise and disappointment maybe, I learned that they really knew most of what we're talking about in the 50s to the 70s, and they were really good at it. Okay? So get this book, follow, this figure is from it. All of these different things are different chapters they have in here, and you can learn a lot in great detail from this. This will help you to choose the right method for the specific material that you're trying to grow. And then this is just one more book that I think is very useful. Okay, so here's a question. When you guys get a new compound or element or something, and you want to know whether it's safe or not, what do? You probably talk to your safety people. And what do they usually say? It's usually something like, oh, you should read the materials safety data sheet, right? Has that been useful for anyone ever? No, because it tells you that everything is going to kill you, right? That's not helpful. So ignore that. Well, don't ignore it, because they will not like that. But refer to something like this, okay? If this doesn't get you to where you need to be, email someone like me. If I don't know the answer, I'll try to put you in contact with someone else. Again, this is just back to this idea that you want to know what your elements are all about. You want to know this book has chemicals in it too. You want to know what your chemicals are all about, and try to just be the expert on this, before you really dive into working with some chemicals or elements. Okay, so moving along. That's all of my general advice.
Can you give us some examples of dangerous chemicals that you might not be able?
I don't know. Well,
of dangerous chemicals?
Sure. I mean, ones that I think this is really obvious, but I will just go ahead and say it. Some elements, when they have high vapor pressures, right, at fairly modest temperatures, well, actually, this is a good point. Like, let's say that you're just a beginning graduate student, you really don't know much. So phosphorus, selenium, tellurium, mercury, these are all sorts of things that we can work with, and we like to have them in our compounds, but they are really dangerous, right? If you inhale some vapor of any of these at high temperatures, it can be a serious health event for you. So, and it's fairly straightforward to actually get yourself into a situation where you would be exposed to that. So let's say that you take some phosphorus and you seal it in a quartz tube and you heat it up to 700 degrees C. I think the vapor pressure by that point is pretty high and it'll burst the tube. When phosphorus gets into air, it forms phosphine gas, or that's what I've read, and that, I understand, is very bad for you. So maybe you have some even better examples, but yeah.
Things like, a lot of us are working with chalcogenide, right?
Right.
Don't treat them with acids, right? You'll evolve H2S, H2SE.
That's good.
Which is
Yeah.
deadly at parts per million.
Right, yeah. So, and I think, maybe I'm spending too much time on this, but it is important to be safe in this way. The point is that no matter what you're starting with, even if you think that it's really, really safe, just read about it first. Yeah. Even if your professor thinks it's really safe, try reading about it first. That can save you a lot of grief. Maybe especially. Yeah. Okay. So any other questions on this or this sort of thing? Okay. All right. So I'm going to move on now and talk for a little bit about this induction furnace technique. Which again, when I first encountered this, I thought that I was being extremely clever, right? But this induction furnace technique is something that dates back at least to the 50s and I'm sure before, right? So everything I'm going to tell you about is very old, but maybe I can repackage it as something that maybe is new to you or was new to me. All right, so what is the idea with the induction furnace? The idea is that you should have, you should make a coil, right? This is shown here. It's some sort of a solenoid. That's attached back to a power supply that generates a radio frequency electrical current. And that goes into this coil. You can dump a lot of power in there. And by the way, this coil is water cooled, so it stays nice and cool. And then by putting this RF frequency signal in here, you generate a magnetic field inside of here. I think that makes sense to everyone, right? That's a really nice situation because now you can take something like a metallic workpiece, which is shown here, insert it into that coil, and then the oscillating magnetic field will accelerate the electrons in the workpiece, and then the workpiece will heat as a result of just ohmic heating, right? I²R. And so this is a really nice way to heat your sample in a contactless way and in a very controlled way. I want to make one little comment about the power supply. When I was a graduate student, the first one of these that I encountered was a power supply that was about this tall and like this big, and it was a very scary thing. It had grounding rods and all sorts of weird things. Nowadays, the power supply that you would encounter would fit on a desktop like this, and that'll get you 6 to 10 kilowatts of power, which is, it's a lot. Okay, so then what are the advantages? Well, you have control over the shape of your coil, right? You will make it yourself, so you can make it very long, you can make it short, whatever. This means that you have very fine control over temperature gradients that you can put in here. You can accomplish really localized heating very easily. This oscillating field actually results in a stirring of the melt. This is extremely advantageous for making your melt really homogeneous, right? And for stimulating crystal growth. I'll come back to that later. But I just think if coming and having a drawer set under your resistive furnace is enough to get your crystals to get bigger, and people are opening and shutting that drawer a couple times a day, how much more can you get by actively stirring the melt as you do your growth? Okay, the answer is a lot. Besides this, you can work with both metals and nonmetals. All you really need is that you have a crucible that is conducting, and then you can put anything you want inside of it. You can reach all sorts of temperatures. This depends on your coil geometry and power supply. In our system, we found it very easy to get to 1700 degrees C, and the only reason that I haven't gone further is that I'm just a little bit worried about melting the quartz tube that's here. I'll describe this in a little bit more detail in a second. And then you can also have very good control over your gas environment. So let me just tell you a little bit more about the apparatus here. It's totally home built. This is, besides the power supply. And this is another advantage here. You know, building something like this is extremely cheap. So if at some point you're a new professor and you're good at designing and machining things, you can build something like this for, you know, a very small budget. Again, like maybe tens of K, something like that. Okay, so what we've done here is to build up a system where we have the coil going on the outside of a quartz tube, and then the quartz tube is attached up to a gas flow circuit where we bring in usually purified argon gas because we want to have metallic workpieces in here. We don't want them to oxidize during the growth. So we flow gas through here. You could put it under vacuum if you wanted to. And then we've just capped this thing with water-cooled flanges on the top and the bottom to try to prevent this area from overheating. Incredibly, it's really the case that even when this is at 1700, the quartz itself is not, you know, like glowing white hot or anything like that. It's pretty amazing. And then what we've done in addition to this, because we like to have control over the location of the workpiece, we've brought in a linear translator and dropped a aluminum oxide rod off the end of it, from which we can suspend the workpiece that we want to use. So you can see this is just designed for our purposes, but in fact you could make more or less any sort of configuration that you like out of this. So I think it's a very flexible way to go about doing things. Okay, so now that I've described it, I think a video is always fun to see. What I'm showing you here is a little bit of aluminum. This is a coil that was wound in one direction and then it's counterwound to sort of stabilize the location of where this thing can sit. Clearly this is magnetically levitating. It does rigid body motion until the thing actually melts. Now it settles down because the inside of this is liquid. And in no time at all, it starts to glow red, right? Which is pretty great. And pretty soon we've got glowing white, which is at least 1200 degrees C, right? And now it's really extremely hot. And I hope no one noticed the feet that were underneath the coil. And I don't remember how long this goes on for, but we're almost there. Okay, so that I think illustrates the ease with which you can do this. And I want to make a few points. First of all, this coil that we used here is incredibly crude. It was wound by Research Experience for Teachers participants back in 2016. And if you're not familiar with Research Experience for Teachers, this is a thing where, you know, teachers at any level come and spend time in your lab for the summer. These two who were working on this, one was an elementary school teacher and one was a middle school teacher. So they had basically no experience in a science lab, and yet they were able to do this with just a little bit of guidance. So I guarantee that graduate students can build this, no problem. Okay, so that's neat. The other thing that I just want to emphasize about this is the very fast heating time, right? We went from room temperature up to maybe 1300 or something like that in tens of seconds. So it's a rapid throughput type of apparatus. You can also consider the utility of this in quenching specimens, right? So you could easily set up something like this that has a quench bucket underneath it, and drop your sample out into that. So that's a nice thing to be able to do. Okay, and sorry?
How do you measure?
Yeah, okay, I was going to get to that, but that's a really good point. Okay, so to measure the temperature is a little bit of a pain. What we do is we have a pyrometer, right? It's an optical pyrometer that we focus onto the workpiece itself. Now, I want to remind you of something. I probably don't need to actually show you, but you know, we have this quartz rod around the sample for our real growths, right? And the trouble with the quartz rod and the pyrometer is that some of the intensity of light that comes out of the sample gets scattered in the quartz rod. So you're not making a truly quantitative measurement of the temperature, you know, when you try to measure it through the quartz. We estimate that the temperature, the readout temperature is different from the actual temperature by about 10%. But that does present some issues. Your actual knowledge of the temperature may be fairly limited. The other thing that you can do, and we haven't done it on our system, but you can make a feed through and run a thermocouple in here. Right? That would be fairly straightforward. The only disadvantage to that for us is that we often do some growths in here that are fairly messy, and so it would involve making thermocouples all the time because they would get destroyed by the processes that we're doing. Okay, so and here you see you can make all different sorts of coils. It's really not too hard. This one was made by a machine shop, but no big deal. Okay, so now let's think a little bit more about the details of how this works. The way that the induction furnace operates is by having some sort of metallic or semi-metallic workpiece in there. This opens the door to using all sorts of different crucibles. These are all examples that we've used. They work really nicely. So for instance, tungsten and molybdenum we find working very well under an argon atmosphere. Nickel is fairly robust even in air. I think people know that platinum you can heat to pretty high temperatures in air and it will be very stable. So platinum crucible is a nice thing to have, especially if you're not just focused on intermetallics. We very often produce tantalum or niobium crucibles. And if you haven't encountered these before, I'm actually going to return to them later and tell you how to make these things. But they're very useful for any sort of reaction that you want to do above 1200 degrees C. So I think that people probably know about the limits of quartz tubes. We like quartz tubes because we can shape them, we can put reactions inside of them, carry them out fairly easily, but they soften above 1200 degrees C. Right? Some very brave people will take them to 1300 degrees C. The way that you can solve this problem is by using tantalum and niobium tubes, and that's a fairly common thing to do. The other type of crucible that I want to mention are graphite crucibles. These are really fantastic. Yeah, question?
But we should somehow evacuate this niobium tube because at the temperature of more than 900 it will react with oxygen and create in a quartz tube.
Well, okay, right. So this was something that I thought would be a problem in a system such as this. But look, in this apparatus where we do have a quartz tube, it turns out that the radiative heating coming off of the sample at 1700 degrees C, where the distance between the workpiece and the quartz is only, something like this, the quartz, which is water cooled to a certain extent, reaches nowhere near the melting temperature. So if you set up something like this where you focus your heat, the heat is really focused on the sample and not on the surroundings, you can reach very high temperatures in the tantalum tube.
Nevertheless, we should evacuate this tube in a quartz, so it should be connected to the static or dynamic vacuum or something.
So I'll mention again, so the way we have it set up, vacuum is fine, but I think it's easier and possibly even better to run this at an overpressure of purified argon, right? And I think, let me say, the reason I think that that's better than vacuum is that if you want to have an extremely good vacuum that's truly going to protect your crucible, you probably can't get away with rubber O-rings, right? You probably need to make an ultra-high vacuum environment. That's difficult and costly. But if you run this at an overpressure of argon, if you have a little leak here, it doesn't matter, right? You can protect your metallic workpiece very well. And we can carry out these reactions on the order of 48 hours, 72 hours in this flowing argon environment and observe very little oxidization on the workpiece.
But do you use industry-grade argon or grade 5.0?
So I don't like the argon directly out of the bottle. And you know, even when it says UHP argon, I'm not convinced that that is very clean. I think that what UHP means in terms of the industry standard is that they used a certain method of connecting to the bottle. I don't think it's the actual quality of the argon. So I think it's very important that you have some sort of gas purifier in the circuit before it comes in. There's a lot of different models of gas purifiers. The most rudimentary type is something where you have a charge of some metallic powder. I forget what it is right now. In any case, it gets heated like a little furnace, and then the gas runs through there, and it gets stripped out of the impurities. You can make very clean argon gas that way. Well, I suppose another way that you could make a clean inert gas is to boil it off of a cryogenic liquid or something like that. But there's ways to do this. Okay. Okay, so what do I want to say? Oh yeah, graphite. I just want to encourage you to think about graphite because especially for the RF furnace, it couples very nicely to it. In addition to that, it's machinable and cheap. So I don't know if you know, but these Illumina crucibles are fairly expensive, and it hurts you to crush them to get your samples out. But the graphite, you can buy a rod of graphite. You can buy from Alpha Acer these rods that are about this long and about this thick. You can buy like 5 of them for $400. And from that you can make many crucibles by sectioning them off and then just using a drill bit, even by hand, and burrowing out a space inside. Now if you don't want to be quite as cheap as that, you can work with your machine shop, and they can make you all sorts of different types of crucibles. And one thing that's really wonderful is that I've found that if you take one like this, that's a barrel, and you have a nicely shaped piston plug that can go in the end, as long as it's a fairly tight slip fit, that can hold in a modest amount of vapor pressure. All right, so it's amazing. But a recent example is that I took some indium that had some other stuff dissolved into it up to about 1500 degrees C. By that temperature, it's over an atmosphere. I expected it to push the piston out and then have the indium vapor come spilling out. It didn't. It held it in there. I learned about this from a former postdoc from Bob Kava's group. They're doing this sort of thing as well, so I'm not just making things up. And it works incredibly well. Okay, so that is a really cheap alternative and easy alternative to trying to seal these sorts of refractory metal crucibles.
What is the maximum temperature can it withstand?
The maximum temperature for graphite?
Yeah.
I mean, well, the question you really want to ask yourself is what does the binary phase diagram look like for the carbon plus whatever you're trying to react. But the graphite itself will go to 3000 degrees C or something like that. So, and I'll tell you, I haven't heated it to 3000, but I've gone to what, like 1700, and its thermal expansion properties are very good as well. It doesn't crack itself, it just sort of goes there and comes back.
Can you always put that thing in place of what's
Yeah, You can put it in quartz, no problem. And one last comment about this, because I'm so excited about it. This piston, the other thing that I thought might happen is that when the vapor sort of gets up around the piston and in between it and the barrel, that it might be then very difficult to get the piston out, right? And that could make your life difficult. But graphite has this wonderful property that it kind of self-lubricates. So getting that piston out is very easy. It just pulls right out. So I would say you should play with this and see what you can do. Okay, and I already told you this story. Okay, so moving along. Okay, so what do we want to use the induction furnace for? I can see I've already chewed up most of my time. That's okay. Okay. So what do we want to use the induction furnace for? Well, first of all, it's a great place to sort of prepare your elements and also to do simple direct reactions of elements. Right, so just as an example, and this is kind of a rudimentary example, but here's some nickel balls. Sometimes your starting material is kind of dirty. You want to drive off some things that it might have absorbed onto it. Maybe I have powder instead of nickel balls. I don't know. I want to clean it up. So one way to go about doing that is to load it into some sort of a crucible. In this case, we've taken Illumina, and I chose this example to tell you one more thing. What we've done is we've wrapped it in some refractory metal foil, right? I think in this case it was niobium foil. And the reason that we did this is that you cannot heat Illumina with an RF field. There's no electrons to move, so it's not going to heat. But you can heat a nice piece of foil, right? And the trick here is just that you should choose the quartz tube to be a similar diameter to the Illumina crucible, so that when you wrap the foil around here, it's touching itself nicely. You don't have to weld it or make sure that it's really a complete circuit. This is good enough to drive electrons around here. Then you heat the foil. That radiatively heats the Illumina. Of course, in this case, this is touching the quartz, so don't go above 1200. And in the end, you wind up with a nice precursor boule that you can use. One neat thing that I just like to point out here is that this process also somehow produced some little single crystals of nickel sticking out in that void there. Okay, so that's nice. Another way that you can use this is just like the arc furnace, where you want to just combine or react some elements.
Sorry, did you say which foil? What foil?
Oh, sure. So we often use niobium foil, but that's only because we have a huge roll of niobium foil. I think you could easily use tantalum or any refractory metal would be just fine. And if you can find something cheaper, that is a good idea.
But it's a one-use thing? You can't use it.
It tends to be a one-use thing, yeah. I suppose that after something like this, where you just melt some nickel, that you could extract the foil and use it again. But on the other hand, if you get stuff like vapor coming out or something, then
Is it obligatory to heat the crucible this way, or just, as I understand, nickel will heat itself?
Yeah.
In the crucible? Because at this point, it should be quite tricky, because this rubbing foil can heat even quartz tube.
Yeah, no, that's a good point. And I guess what I would say in response to that is that you could try. You could try. It's not obligatory. You could try. I have had the experience that I put things into the Illumina crucible and then I am not able to heat them as effectively as when I have the foil on the outside. I would say try it without the foil. If it works, you're done. And that's the simplest and best. Yeah. Okay, so then of course you can do direct reaction like this. This is just something, actually I think this is from an arc furnace reaction, but you can use this in exactly the same way as the arc furnace. And then I wanted to tell you one more thing, and I didn't have a way to make a single slide about this, but very often we're interested in having single crystal specimens, but you don't have a good apparatus to make the single crystals that you want. Okay, so let me tell you a poor person's way to get a single crystal flake of something. It can happen that your arc melted or induction furnace grown boule actually forms large grains, right? You've probably seen that before. So then, if it does that, and you're willing to do the work, you can take just a little hammer and tap this a little bit until it cleaves apart. And then looking under the microscope, maybe using a light polarized microscope, like a Nemarsky filter, which is helpful, you can identify pieces that at least on their surface are a single grain. Okay? Then you can take that to your Laue single crystal X-ray diffractometer, which everyone has and is familiar with, I'm sure, and immediately learn whether or not you've actually been able to get a single grain piece out. Okay, so that's fine. Then all you need to do is flip that piece over, polish it, make a measurement from the other side. If both sides look the same, is a good chance that you've got a single crystal piece now. And this is a very useful way to make things if you don't have the resources of like a large Czochralski crystal growth apparatus or something like that. Okay, so moving along. Okay, so another way to get single crystals, and this is probably the more well-established way of going about doing it, is using a Czochralski technique. So how many people know what Czochralski crystal growth is? Okay, so few enough that I should describe it. So the idea behind Czochralski growth is that you should make a puddle of liquid metal, right? And I don't care how you do it. You can use focused light, you can use an arc furnace, you can use an induction furnace, which I've shown here. I think most commercial apparatuses are like this, where you have sort of multiple arc stingers to heat your sample, but it doesn't really matter, okay? So you make this puddle of liquid metal, whatever you're trying to grow, and then what you'll do is you'll insert into it something that's not going to melt in the liquid metal, dip it into the liquid metal, and then slowly pull it out. And in so doing, you can extract a single crystal grain sometimes. It's hard. And the point that I want to make here is that the induction furnace gives you a very nice way to accomplish this sort of situation sort of on the cheap, right? So these types of apparatuses are really nice. They're wonderful. You can make beautiful crystals in them. They're also extremely expensive. With a little bit of ingenuity and accepting that it may not be perfect, you can build up a nice Czochralski crystal puller within an induction furnace as well. So if you become an assistant professor someday and you don't have a lot of money, you can think about doing it this way. Okay, and another video. This is ours in action as we were developing it, and we are still developing it. But what we've got is a Illumina rod. We've sharpened it to a point. We have a tungsten crucible. There's a Molten here. And then we've started to pull a crystal out of here. You probably noticed that this growth failed, right? The crystal separated from the melt. But at least it illustrates the principle that you can pull crystals out this way. Okay, now here's some examples of things we've been able to do successfully. Okay, and coming up on the end, I want to tell you another use for this. So you can also use this setup for any sort of Bridgman growth that you might like to do. This is why we have a crystal puller on here in the first place. So the idea is that you may take a crucible and have a sharpened point on it, and then load this crucible with a polycrystal of whatever it is that you're trying to grow. You should bring it into the hot zone. We can generate it with the RF field and liquefy all of this material, and then slowly withdraw it from the other end. And if things work the way that you hope they will, a single grain will nucleate out of the bottom of this tip, and then it'll propagate up through the entire crucible. This is actually more challenging than it sounds, but it's a good way to get big crystals. Okay. Okay, and my last topic for the induction furnace, I want to tell you about how it's useful for molten metal flux growth. So I already touched on this, and I think that there's probably enough people here that are familiar with molten metal flux growth. The idea, just to reiterate, is that you will take some low melting temperature element like indium or tin or aluminum, whatever you like, and you will heat it up and try to dissolve some higher melting temperature elements into it until the melt is supersaturated. Right? So, I don't know, an example, uranium, ruthenium, and silicon, dissolve them into indium. Then you'll slowly cool down the melt, and single crystals will start to precipitate out of the melt. For anyone that hasn't done this before, it's like growing rock candy or borax candy. It's not candy, but you know what I mean. Don't go home and eat borax. Okay. Right. That's a really great way to grow single crystals. People do it all the time. It's wonderful. But there's one problem with it that was always frustrating to me, and that's because I have a very short attention span, and that is that it takes a long time. You usually let those things cool down over the course of a week or 2 weeks. And especially, if you're trying to do a PhD, this might be a problem, right? Like your growth doesn't work and you have to do it again. So pretty soon, a month or 2 months have gone by. And that's too long. So the thought that I had, and again, this wasn't original, I found out later, is that because the RF field provides a lot of stirring, this might actually be able to accelerate a molten metal flux growth. And so what we do is that we'll carry out this sort of growth, for instance, in these sealed tantalum crucibles. We'll suspend them from a pull rod, this Illumina pull rod, put them into the hot zone, take the system up to whatever maximum temperature we want, and then over the course of, it can be as short as a day, but maybe we want to go for 48 hours or something like that. We'll slowly extract this from the hot zone. And so now, in contrast to what you have in a box furnace where you have, there's some temperature gradient, but not a whole lot. And you're ramping the temperature down by changing, the temperature of everything sort of all the same. We're making this temperature change in a crucible that has a pretty strong temperature gradient on it, right? I think that's helpful for crystal growth. At the same time, we're stirring this melt like crazy. And kind of as I hoped, the way this turns out is that you're actually able to produce nice single crystal specimens. They're not usually huge, but they often can be comparable to what you get out of the more conventional type of molten metal flux growth. This is just one example. We're focused on uranium, ruthenium-2 silicon-2, which is an interesting compound. We see that making pieces from either method is pretty comparable. So nowadays, when it makes sense, we like to do our flux growths in the induction furnace. One final comment about this, just keep in mind that when you do your flux growths in a box furnace, you're always limited to 1200 degrees C because you don't want to melt your quartz tubes. In this situation, you have a whole new arena of temperature phase space that you can now access. And if I had more time and money, I would be looking out into that part of the chemical phase space as a nice place to look for, new materials. I think it's a useful way to do that. Okay, so should I stop here, JP, or should I keep going?
Yeah, we should probably stop.
Okay, so everyone knows about arc furnaces, and I'll leave it at that.
Unless you have a few tips.
Okay, quick tips. Okay, so I'm not going to tell you about what an arc furnace is. I'm going to tell you that one thing that it's really useful for is preparing your precursors. You may sometimes have a powder or a granular form of something. You may think that it's very clean. I can tell you it's probably not unless you live in the high desert or something. It's definitely not true in Florida. So what we do is we take these powders, we arc melt them, drive them into boules, and very often we see these halos of junk that was, absorbed into the powder. I think that's a very helpful thing to do. Now, I wouldn't claim that even this arc melted piece is really like ultra high purity. but it's certainly much better than what you started with. Okay, so that's one thing. They're useful for making binary fluxes. You know all about that. Polycrystal synthesis. Yeah, I want to tell you this. So last thing, I've talked a lot about these tantalum crucibles. They're fairly straightforward to make, but you really need to know one trick. So if you want to make these back at home, do the following. Start with a tube. You don't want that tube wall thickness to be too thin. The reason for this is that tantalum, when you get it to be liquid, is not very good at wetting to itself. It'll form beads, but those beads don't like to wet to each other. Okay? So if the wall thickness is too thin, it's easy to sort of punch a hole in it and you're out of luck then. Okay, but that's not all. So what you want to do is take one of these tubes, cut off a piece using just a regular pipe cutter, and then here's the most important thing. Now you need to close the end. It's insufficient to just press the end closed and then try to weld it shut. And the reason for that is, again, this wetting property of tantalum. If you do that, you press it and then bring like an arc across the end of it, what it'll do is it'll kind of pull back from itself, right? And it'll leave holes in the bottom of the tube. So what I've tend to do, and I think this is a really good way to do it, is you press the bottom using, just a vise or something, and then you make this little fishtail. These ends are bent up, right? So there's a little triangle here, and these are pointing up. And the idea here is that now, when you bring the arc into place over this, you're going to have gravity on your side. And so the bead that you make, start on one end, and the bead that you make will start here, and it'll roll down into the middle. And same thing for the other side. And this gives you a much, much higher success rate in making well-sealed tantalum tubes. And so you arc melt it, you do the same thing to the other side. Don't worry about the quartz, that's just an example. And this brings me to the end. I just want to make, I thought I changed this slide, oh well. So some words of encouragement. I think, we've talked about this idea that we're all going to pursue some sort of central concept in science, but in order to get there, we need to have the right toolbox. And sometimes we even need to make tools, right? So keep in mind that you have the freedom to make a diverse toolbox. That's probably key. And then I think that one of the great things about being able to do crystal growth and so on, sort of put together by or stated by Bernd Matthias, who's sort of the godfather of our field. So he said, with respect to crystal growth, even a blind chicken can find a grain. And I think that's true. So, or to quote someone else, it's a new day, so why not put another batch in the furnace? And that's the idea. Okay, thanks.